Modern computers not only have a very powerful CPU, they often also have a very powerful GPU. And where a typical Haskell application might have tens or maybe hundreds of threads all running, doing different things, a typical model for a GPU is quite different. We might have thousands or even hundreds of thousands of threads, but all doing very similar things. So the programming model is rather different. And in today's episode of the Haskell Unfolder, we're going to take a look at Cuda. We're going to see how we can set up a build environment so that Cuda and Haskell can work together. We're going to take a look at how we can call Cuda functions from Haskell. And we're going to take a look at how we could test Cuda functions using QuickCheck and why we might want to do so.
Yeah, welcome to the Haskell Unfolder, a YouTube series where we discuss all things Haskell. As always, the show is live streamed, so we invite you to submit questions or comments in the chat, and we'll try to show them on screen and discuss them.
Right. So in this episode, I want to develop a very small Cuda library. And the point of the library is not to outperform Haskell in any way. The point of the library is more to give you a taste of what Cuda can look like, the kinds of things that we need to think about, that sort of stuff. So we're going to define three functions: a map, which is going to add map add addition over a vector of floats. We're going to add value x to every float in the vector. A fold, which is going to again fold with respect to add, and a scan again with respect to add. Now, before we take a look at how to actually define any of these functions, I want to talk briefly about how to set up our build environment. Because when we define code in C, we can actually do this in Cabal, right? We can just add some C files. Cabal knows how to compile them. That's quite simple. But with Cuda, that's not the case anymore. And so we need to build the Cuda code ourselves, and then we need to somehow tell the Haskell application how to find the Cuda code. And the cleanest way that I know of doing this is through a package config file. So a package config file is a Unix thing. It's basically a description of a library that's available on the system. It has a name, a description, a version. All that stuff is not really that relevant. But two very important things here is it tells the compiler some flags, in particular where to find any include files that we might have. In our case, that's this particular include file. And it tells us which library to link against and where that library exists. And the critical thing here is that the include directory and the lit directory are both defined in terms of some prefix, and I have not defined what that prefix is. So this is an incomplete file. That's why I call it pc.in. And what the make file does for this small Cuda library is it just constructs a file where the first line is the current working directory of this whole thing, and then the rest is just the rest of this this thing here. So if we take a look at what that looks like, is just exactly what you'd expect, but with the prefixes now the exact directory where on my local machine, where this directory is installed. And the whole point is that on somebody else's machine, somebody else who checks out this repo, all those paths will be different, but everything will still work as fine as expected. And so then on the Haskell side, we need to say Haskell Cabal supports package config directly. So we have, say, we depend through package config on this library called app38 Cuda, and then it will invoke package config to find the appropriate flags. It does mean it needs to be able to find where this package config file lives. And so in my Haskell directory, I've set up some paths. In particular, the package config path includes the path to the Cuda library, and the library path, this is important when you run the application, also includes that. So this is, that's a bit of a whirlwind. You can find all the details in the repo, but I just wanted to point this out that this is a way we can set things up. Everything will be resolved appropriately on everybody's local machine, depending wherever their paths are. And there are no absolute paths or specific assumptions in the repo. So I think this is just a clean way of doing it. And one other thing that you might need to do is I have a Cabal project.local file here, which tells Cabal where the Cuda libraries live, because the other thing that we depend on is the Cuda runtime. And that on my particular machine, that lives in a specific directory, which is not the standard system library directory. And so I need to tell it where that is. Okay, that's by means of introduction. Let's look at some actual Cuda code now. So let me just close all these files here. Let's take a look at map first. So what is map going to do? We're going to define this C function here. which is just, at this point, it's just a regular old C function. It's going to take a value x, which is the value that we're going to map across the array of floats, the actual array itself, then a pointer to the array that we're constructing. So we're not doing this in place. We're building a new array as we're used to doing in Haskell, and then the size of this array. And the contract here is that the Haskell code is responsible for allocating the output array. We could allocate it C-side, but my recommendation whenever you do anything like this is, whenever possible, pre-allocate everything in Haskell side. Otherwise, it's quite difficult to do this in a way that is guaranteed to be safe, even in the context of asynchronous exceptions, things like this, and you don't leak memory. So if you can allocate Haskell side, it's better to do so.
Right.
Okay.
So really, we are getting like pointers to two arrays, and it's just policy that we treat one as input and one as output, right?
That's right. Yeah, that's right. There's nothing in these C types that tells us that is the case. Yeah, that's right. Okay. Now, these arrays, in particular the input array, lives in memory on the machine, right? On the CPU memory. That means that our GPU can't actually access it. The GPU cannot access any memory directly on the CPU, the main memory. And so the first thing that we need to do is to actually copy this input array to the device. That's also why this underscore h is here. This underscore h here is a reminder to ourselves that this thing lives on the host, right, on the main machine, not on the device. So we're going to make a new array, and we're going to allocate this on the GPU now. And this is going to be an input-output array. So we're going to update this guy in place. That's okay, because we're going to copy the array, the input array, to the GPU. We're going to update it in place, copy it back to our new array, and then we're done. Okay, so we need to figure out how big this array needs to be. Well, that's just the number of elements in the array times the size of an individual float. Okay, and now we need to allocate this. Now, this is not a normal malloc, right? Because a malloc would allocate it on the main memory. We want to allocate it on the GPU, right? So we have a special function for this called Cuda malloc. And it wants a pointer to the pointer where it's going to store the new address and how much to copy. Okay. And sorry, how much to allocate? Sorry. And now we do need to do the copy, right? Now we have some memory allocated, but there's nothing in it yet, at least nothing defined. So we need to copy into our input-output array, which the underscore d says on the device, right? From our input array number of bytes, and then we need to tell it the direction. So in this case, we're going to copy from the host to the device. So Cuda memcopy host to device. Okay. Now we're going to do some magic here, and we're going to actually run some code on the GPU. But I'm going to skip that for just 1 second. And then once we're done, then this input-output array lives on the GPU memory. Remember, it has been updated. Then we need to copy it back, right, into our output array. So we're going to copy now into our output array from the input-output array on the device. Yeah, go for it.
So just from a Haskell perspective, because I mean I'm used to having more type safety, right? I mean, so,
yeah.
So
it's very low level.
We have to give the direction because, like, from the types in out D and in H look exactly the same, so it wouldn't know, right, which one.
That's right.
It wouldn't know which one lives where. So.
In fact, it's even worse than that, because the type of this guy is just float, pointed to a float, right? We don't even know that this thing lives on the device. Right? This is not the type level.
Exactly. Yeah.
So the types don't tell us anything, and the runtime value, the actual value, are literally just just addresses. And so we can't even look at the address to figure out.
So things would go horribly wrong if we got the direction the wrong way around.
Yeah, we would overwrite our input array with random values. Yeah, exactly. Okay, good. So the idea is we have some stuff living on the main machine. We copy it into the GPU, do some calculation there, and then copy it back. Now, of course, doing all that just to map over it, like over a couple of elements, is not going to be worth our effort, right? Then the overhead of doing the copying back and forth is way too high, right? But that's not the point of this episode, right? We're not. This is just to give you a flavor. But normally what you'd want to do is copy some stuff to the GPU, do a ton of calculation there, and only at the very end, copy it back. Anyway, okay, so what are we actually going to do on the GPU? Well, what we're going to do is we're going to spawn a thread for every element of our input array. And that's maybe a bit surprising. That's like that level of granularity is unexpected, perhaps, if you're not used to GPU programming. But on the GPU, it's normally just fine. So we're going to define some code now, and which is going to run on the GPU. The global prefix here says this lives on the GPU. I'm going to call it map add kernel. A kernel is something that runs on the GPU. It needs to know what to add, and it needs to have a reference to this input-output array. Now, like I said, every thread is going to run this code, right? And so we are actually given something called a thread index value. And we're just going to use the thread index, just going to run from 0, 1, 2, 3, right, all the way up to the number of threads that we have, as our index into the array.
Okay.
And now all we're going to do is we're just going to update the array at that thread index. And that's literally all. This is literally the entire code, nothing else. So the last thing we need to do is actually run this, right? And so we're going to call our kernel, but this is not a normal invocation, right? This is like run this on the GPU. And there's a special syntax for that in Cuda, which has these angular brackets, and there's some arguments in between, which I'll talk about in just a second, and then the regular arguments. And the regular arguments are x.
3 on both sides? Or?
Yes, thank you. Yeah, well spotted. Yeah. So the arguments here are, the second argument is how many threads we want, in this case is n, and the first argument is how many blocks of threads that we want. And so if we spawn 2 blocks of 100 threads each, we're going to get 200 threads in total. In our case, we're just going to spawn 1 block of n threads. That does mean that n is limited to be maximum 1024. Most introductory Cuda books will tell you how to generalize this to many blocks, things like this. I'm not going to do that in this episode. Like in this episode, we're always going to work with only 1 block, just to keep things a little bit simpler. Anyway, that's it. That's all we're going to do for our Cuda code here. So let's just build this. It's going to call NVCC, which is the Cuda compiler, and then it rebuilds the shared library. And now on the Haskell side, we need to actually call this function. Right now, this C function, this is a regular C function, which takes what? A float, a pointer to a float, a pointer to a float, and an int. Right? Okay, so we can do that easily enough, right? That's float, pointer to float, pointer to float, int to IO. Okay, this is the actual foreign call. But this is not a type that we want to work with in Haskell, right? This is very low level. We don't want to think, we're not usually thinking about pointers or anything like that in Haskell. So instead, one option is to use a storable vector. So a vector is a package which is very common in the Haskell ecosystem for arrays, right? Contiguous blocks of memory. And storable vectors are basically the representation of a storable vector in memory is exactly identical to that of the C array. So it's very suitable for doing foreign function calls. Okay, so how do we now define this thing, right? Because we get some vector, we want to return a new vector. How do we define this in terms of the low-level function here? Well, we're going to get x and some input here. Now, the first thing is that this doesn't need to live in I/O, right? This guy lives in I/O, but this doesn't need to be. Why? Because, well, morally speaking, these are a pure function, right? For the same input vector and the same value x, we're going to get the same output vector again, right? So this doesn't need to live in I/O. So this is a case where we can tell the type system, yeah, we're going to run some stuff in I/O, but trust us, this is okay. You can pretend that this is a pure function, right? That's what unsafe perform I/O does. Relatively common when you write for a function code. Not so common elsewhere. Okay. Now, what do we need to do to actually call our function? We need a pointer to these floats. Now, fortunately, the point of using a storable vector is that it gives us precisely that ability to get that pointer. So we can call unsafe width on this input vector, and it will give us an input pointer. It's unsafe because this pointer, you really shouldn't escape the scope of unsafe width. You need to be careful. You really shouldn't be modifying this stuff, right? You can do all kinds of stuff now that would break internal invariance of the vector, but as long as you're careful, you can use this pointer. Okay, so that gives us the first argument, the first pointer. We also want to allocate a new array, right? And I said we're going to do the allocation Haskell side. So let's now actually do that. And we're going to use malloc foreign pointer array to do precisely that. Right, so this does exactly what it says on the tin, right? The name is very self-descriptive. It needs to know how many elements, and then the number of bytes will be n times the size of each individual element, in this case floats. Now this is a foreign pointer rather than a pointer, and the difference between the two is that a foreign pointer has a finalizer attached to it. So when this falls out of scope, when the garbage collector says, oh, this is no longer needed, it will free this thing. So we don't have to worry about it, right? We don't have to worry about freeing this. We can depend on GC to do it. So that's convenient. But we do need the actual pointer out of it before we can call our C function. So that is called with foreign pointer. And now we have an honest to goodness regular pointer. And now we can call our C function, right? We have an input pointer, an output pointer, so we can call our C function as this. Of course, we need to know exactly what n is, right? How many elements are in the array? Well, that's easy, right? That's just the length of the input vector. Okay. And then finally, we now have an output foreign pointer, but we want a storable vector out of it. But there's a function to do precisely that. So we can say unsafe from foreign pointer 0 out foreign pointer n, and we're done. And again, this guy's unsafe because if you then actually modify some of the elements in this vector through this pointer, you lose reference transparency, things like this. You need to be careful, right? So, but we're not doing that. The output vector is the output pointer is gone, so we can't. This is actually safe. And the 0 here means that we don't need any kind of offset. Right? It's in principle you could have a pointer plus some offset if it lives somewhere else, but we don't need to worry about that here. Okay.
Yeah, reasonably straightforward, I think.
Yeah, I think so. Good. So we now have seen how to set up the build system so that our Haskell code can find the Cuda code. We now have seen how to call Cuda from Haskell. Let's actually test this code using QuickCheck. So in order to test this, we need to generate random values, right? How does QuickCheck work? Well, you generate random input values, and then you call a function on those random input values, and then you verify that the result is what you expect, right? So you typically have maybe an alternative implementation. In our case, we might have a pure Haskell implementation that we can compare against our supposedly highly optimized low-level Cuda implementation, right? And then check that they compute the same results. So let's actually do that. I'm just going to copy and paste a little bit of code here. So I'm going to define a new type, which is called small array, which is just a storable vector of floats, which is exactly what we want for our inputs, right? Along with some auxiliary functions that turn this thing from a list, create a small array from a list, or take a list from a small array. And now we need, in order to use this as input to our tests, we need to have an arbitrary instance for this small array. Right? What does that mean? It means that we need two things. We need to be able to generate a random value of this array. That's important, right? Otherwise, how do we generate random values? And two, we need to be able to shrink those values. That's also very important, right? What does that mean? It means that if we find an example, a randomly generated array for which we are getting an unexpected answer, probably because it's randomly generated, there's lots of additional detail in that example that is actually not critical to our test case, right? So it's very important that we then try and shrink that as much as we can so that the counterexample that we get is as small as possible, right? So that we don't spend our time debugging going down the wrong path. Okay, so these two functions are quite simple. To generate a random one, I'm just going to pick an array between 1 and 1024. We can't have 1 and 1024. 1 just avoids some edge cases that I didn't want to worry about in this episode. And then just n times generate a random float, and then just turn the thing into a small array.
Right. The size constraints are the main reason that we cannot completely reuse the list of floats.
That's right.
Arbitrary instance, right?
That's right. Yeah. Otherwise, we could just generate a random list of floats and then turn it into a small array. Yeah, that's right. However, for shrinking, we can actually just piggyback because shrinking never extends the size. So we can piggyback on it. We do need to be a little bit careful. right? So this is a shrinker. It just turns the thing into a list, then shrinks that list. So this is now the standard shrinker for a list of any things, which is going to either try and throw elements out of the list or shrink individual elements, right? So we might go from 3.4449 to 0.1, right? Something simpler. And then we don't want empty lists still, so we filter those out. And that's it. Okay. So that's the first ingredient, right? We can now generate random inputs to our test cases.
Now we need a property.
We need a property, right? Yeah, so we need a property. Now, what's the property going to do is we're going to call our Cuda code, and we're going to compare the outcome to some result that we compute in Haskell, right? In normal functional Haskell code, which might be less performant, but much easier to understand. However, these are lists of floats. And when we are comparing floats, we have to be careful. In particular, we're going to see in later examples that the way that, for example, if we're going to add up a bunch of floats, then the order in which we add them up can result in slightly different results, right? There might be rounding errors that we get. And so we can't insist on direct equality. And so there's lots of different ways that you can do this. I'm going to do something extremely simple for the benefit of this episode here. This is maybe not what you might want to do in real code, but it's good enough for us. Right? I'm going to define this class called roughly equal, which compares two values of the same type. And when we're comparing floats, I'm just going to check that the difference between them is not more than 0.01.
Quite a high degree of tolerance.
Yes, very high. Yes, very high. Yes, exactly. So this is probably almost certainly not what you want in real code, but for us, it'll do. And then importantly, how do we compare a vector of these things? Well, we check that they have the same length and that each of the elements are pairwise roughly equal. And that's basically it. So now test roughly equal just takes two values, compares them, checks that they are roughly equal, and if they're not roughly equal, it gives us a counterexample, says that the expected value is not equal to the actual value. Okay. That's by means of infrastructure, and we're going to use that infrastructure for all the three functions that we're going to define. So now we can actually define our property. So we can say we need to give the property a name. I'm just going to call it map. It's going to get two arguments, right, which both will be randomly generated, which is the array of values and the value that we're going to add. And then we're going to test the two things that are roughly equal. The first thing is the model, right, the Haskell implementation, and the second thing is the Cuda code. Okay, and what is the model? Well, actually, this is very simple, right? It's just a map, so we can just do exactly that, right? So we just say vector.map plus x over our input.
Yep.
Okay. And I already built the Cuda code. Cabal is not very good at picking up changes to C libraries, so I'm just going to clean, and then I'm going to run the code. So it's going to build, and then it's going to run this test, and it's going to run 100 tests by default, and just checks that they are all equal. And in this case, they are all equal. Now, just to show you what happens if we introduce some sort of bug, and let me just introduce a very obvious bug, right? Like, I'm going to add x to every element except for the fourth element. So as long as I is not equal to 3, I'm going to do this, but not for the third element, or for the fourth element, I'm not going to do anything at all. Okay, so let me rebuild this, and then also rebuild and run my Haskell code. Now, when this runs, we expect to get a counterexample, right? And if you think about it, what should that counterexample look like? Well, did I make a mistake? Oh, sorry. I made this mistake earlier during preparation as well. Not equals to is not.
Oh, yeah, I don't know.
That took me forever when I was doing it.
Oh,
I'm so glad that I did that not live. Well, I did it again, but that I figured out, yes. Okay. Let me see if I can get the actual. Yes, okay, good. So if you think about it, for the first 3 elements, we're going to do the right thing. So our counterexample must have at least 4 elements, right? And if you look at our counterexample, it has 4, exactly 4, right? Not more, right? Because just the minimum that we need. And also the values inside this array shouldn't really matter, right? We just want the simplest values possible. And again, that's exactly what we get. Like we get zeros. Now, if I disable shrinking, I might get a much more complicated counterexample. Yeah, like this is the example that I generated. And you can imagine that if you start looking at this and say, oh my God, what's happening here, right? This is pointless, right? So shrinking is definitely very important.
Mhm.
Okay, good. Let's move on now to something slightly more complicated. Let's think about fold. And in particular, we're going to fold concurrently.
You want to correct your map version again? Do you still need it?
That's my part. Yeah, that might be a good idea. Yeah. Otherwise, we'll keep getting counterexamples. Yeah. Good. All right. So what does fold do? Right? Fold, in our case, fold with respect to add is going to just add all the elements in the array for a final answer. Right? And the key to doing this concurrently is realizing that we can start folding anywhere. We can start adding anywhere at all. And so I've tried to come up with a simple diagram here explaining what's going to happen. Right, so imagine that we're going to start with an array, which is any number of elements, in this case 13 elements, which is not necessarily a power of 2. The first thing we're going to do is we're going to find the largest power of 2, which is strictly smaller than the size of our array, and we're going to add elements into this. Well, sorry, let me repeat that. Let me rephrase that. We have 13 elements here. The biggest power of 2, smaller than 13, is 8. So we're going to compress basically all these values into 8 values. How are we going to do that? Well, the first value becomes the sum of x0 and x8. The next value becomes the sum of x1 and x9, and so forth. And so since this is not a power of 2, there's going to be some elements that are going to be unchanged, and they're just unchanged. Right? Now I'm showing this as a series of steps here. In reality, this will be done in place, right? These will be updated in place. Now we're going to repeat the process, but now we don't have to worry about this edge case anymore. Now this is always going to be a power of 2. So we're going to, this element here is going to be the sum of the first element and element number 5 here. This one will be the sum of the number 2 and number 6 and so forth, right? Then we go again one more time. This will be the sum of number 1 and 3, 2 and 4, and then we do one final addition, and that's the final result. And so the entire computation takes log n steps to do the rather than n, linear n, to do the computation. Okay. I'm going to show this in 2 versions. And the first version is going to work only for 32 elements, of arrays of 32 elements. And I'll explain in a second why that is the case. And I'll show you the kernel first we're going to have the same boilerplate like the copying back and forth, but let's look at the interesting code first here. So this is going to be our Cuda code that does this. And remember, this is going to be running up to 32 elements here. In fact, this is going to run for exactly 32 elements, independent of the size of 32 threads, rather, independent of the size of our array. So what do we have? We have this input-output thing again, which is initialized to be our array. And we are also told how many elements are in this array. Then we're going to check if our thread index, which could exceed the number of elements we have in an array, but if it doesn't exceed it, then we're going to set some local variable to be equal to the corresponding input element from our input array. All 32 threads are going to do this. Then the first 16 threads are going to do a copy, right? And this are going to do like this copy here, right? So this red line here, I'm calling the stride in the C code. Right? So you reach across stride elements away, and you're going to add them to the element here. So the stride starts at 16 because we have 32 elements, and we halve it every single time until we reach 0. So what are we going to do? We're going to take our local value, and we're going to add the corresponding value of the thread which is stride elements away. Now to do that, we have this very strange function called shuffle down sync. I'll refer to the documentation for all the details, but the intuition here is quite simple. It just says, give me the value of val in the thread that is exactly stride elements away from our thread. And that's what this does. So every thread does that repeatedly, right? The stride decreases, and at the very end, this thread here has the final result. Right? And so we copy our value, the first thread only copies that value back into the output array.
Mm-hmm.
Okay.
I mean, not completely sure whether you actually said this, and I mean, most of the audience may actually know this, but sort of like the whole point of the execution model is that all threads have to do exactly the same thing effectively, right? I mean, that's so we have to write the code in this way, but it also means in particular that if you have a lot of branching, then that is actually relatively bad, and you want to avoid that, right? In general.
That's right. Yeah. So all and we'll talk a little bit more about that when I show the other code. But yes, that's absolutely right. We can have hundreds of thousands of threads, but like I said in the very introduction, they should all do similar things, right? And if one goes off and branches, then the other threads are just waiting. So branch divergence is something to definitely be avoided. That's also one reason that we are accumulating all these intermediate values here to the left. And so that means that we have all these threads here are working. All these threads that would have done something previously are now all idle.
But it's also one of the reasons why you're not saying in the very beginning, like, if my thread index is this, then I'm going to do this bunch of stuff, and otherwise I'm going to do a completely different thing.
Yeah, that's right. Yeah, that's right. You want to keep your threads as uniform as possible.
Yeah.
Okay, so I said that this code is specifically for the case that we have at most 32 elements. So now let's look at the code that that is general, right? Well, we're still within one block, right? So it's still up to 1024, but within one block. So this is the more general kernel, and it starts the same way. Like we get the input-output array, the number of elements. As for map, we use the thread index to see which element of the array we're responsible for. And again, we start with the stride. The stride is initialized to be the number of threads that we have, and then up to 16, because at 16 we can, in this particular example, we're going to use our code here. And theirs is the same, right? We divide by half. Now we don't have the shuffle thing available for us, so we actually just need to read the value that we want to add from the array that we have, and we just add it to our current value. Now, as this stands, this code has a bug. If you know Cuda, you will realize this. If you don't, you might not realize it. So let's leave it as is for now, and let's just see that we get a counterexample. Sorry, I haven't filled in the blanks here yet on our C code here. So that's really simple, right? We do the same thing that we did before. So we make allocate an array on the GPU, we copy it. If we have less than 32 elements, we use the first version that I showed you. Otherwise, we first use the second version, then the first version, and then copy it back. Okay. So there's nothing much new here. And I need to define what full warp means. I thought I left that in. I guess I deleted it. It's just an argument to this guy here. Okay. So again, I need to clean because it doesn't know. Now I need a property, right, that we're going to test. Yep. And I need to actually call this guy.
Yeah.
But there's not really much new here, so I'll just copy and paste this in because it's actually rather very simple. And in fact,
it's simpler, right? Because we don't get an array out.
That's right. Yeah. So we get a normal float out. So all we need to do is get a pointer to the input array, and then we can just call our C function as is. Yeah, that's right. So it's a bit simpler. Now, what is the property? Well, it looks very, very similar. As in the map case, we have some input array, some randomly generated input array. We call our Cuda fold, and the Haskell model is just a regular Haskell fold. Right? So, okay. Let's run this and see what happens. Now, it gives a counterexample, and it's a rather large one.
Yeah.
Right? Which is surprising, right? So it says that, okay, it was unable to shrink this any further. Now, I said before, right, that's if it can't shrink, that means that the smaller counterexample, the smaller version of this array was not a counterexample. It's kind of surprising, right? Like, what could possibly be the case here? Let's run this again. And now we get a different counterexample, right? Before we had like a 0.8 here at the end, now we get something different here. So not only is it very large, it's also non-deterministic. Now, when you get counterexamples like this from QuickCheck, they're not shrinking properly, and it's non-deterministic, then probably you have a non-deterministic bug in your code, right? If your code sometimes works and sometimes doesn't work, you could imagine that we generate a counterexample for which the code doesn't work. We then try and shrink it, run the code again on a smaller counterexample. It happens to work because it's non-deterministic, and therefore it concludes, oh, I wasn't able to shrink it anymore. Right, so this is a very clear indication that we have a non-deterministic bug here, which is exactly what is happening, and I'll explain why. So in our first version, this code is actually correct. And then this goes to something that Anders was alluding to earlier. All the threads are sort of running very together. Now, that together, what that means, when we are within one warp, which a warp is a group of 32 threads, they really are running in lockstep. Right, so all the threads in the warp are running this. Then they're all doing this. They're all doing this comparison. For the threads for who that is correct, the comparison matches. All the threads are running this. All the other threads are waiting. All the threads are running through this loop all at the same time. Right? There's no divergence ever. Right? Which is also why there's no race conditions here. Once we are outside a single warp, that's not the case anymore. Right? Here we might have different warps, and some of those warps might be run in any order. And so it's possible, right? If you look at this picture again, right? We're doing a couple of successive steps. If we're still updating this element while this guy's already reading from it, well, then we're getting into trouble, right? Yeah. It's very important that we are always waiting for all the threads to terminate before we go to the next step. And so that's exactly the bug here. And so we can fix that bug by inserting a synchronization here, right? So at the end of every step in the process, like for every stride, where all the threads are going to call sync threads. What this means is that we're all waiting for all the threads in the block to run to get to this point, and only then do we continue. That's also, by the way, why we are currently working only with one block, because synchronization across blocks is basically gets much more difficult. You don't have something like this. You need to work with atomic operations, compare and swap, that sort of thing, right? But yeah. Okay, so that was the bug. So now let's try that one more time. Build our Cuda code here, clean our Haskell code, and run it again. And now the test pass. All right, good.
Nice.
Now, I'm aware that we're already well over time, so I have one final example, but I'm not sure that we should cover it. What do you
think so. I think we should. Yeah.
Okay. All right, okay.
I mean,
okay.
People can always drop out.
That's you must say. Fair enough. Okay. Right. Okay. So then let me show you one final example. Scanning. So remember what scanning does is, if I have an array of values, the first element of my output array is going to be the first element of my input array. The second element is going to be the sum of the first two elements. The next will be the sum of the first three, the first four, and so forth. Now, in Haskell, as a Haskell programmer, we tend to think of scanning as something very iterative, right? You start with the first element, you iterate your operation, and you iterate it again, and you iterate it again. So it's not exactly clear how we can do this concurrently. But if we are scanning something like addition, just like for fold, we can start adding anywhere in our array, right? And so that's the key to doing this concurrently. And again, I have another picture for you here, which hopefully is helping.
See, I would have been very sad if you had drawn this without being able to show it.
Well, thank you. I appreciate that. Right. So I have colored the part of the array that's correct, has the correct values in blue. So to start off with, the first element is already correct, right? Because it's the sum of the first element, right? Okay, good. Then what we're going to do, for every element, we're going to, for example, take this element here, this second element here. It's going to be the sum of the first two. This element here will be the sum of number 2 and number 3. This will be number 3 and number 4, and so forth. Now for 0, there is no element here, so it will just stay unchanged. Okay, so now the first two elements are correct. Then, and again, this reaching across, I'm going to call this stride. We're going to double the stride, so now the stride is 2. So for every element, we're going to, the value of every element will be computed by being the sum of its current value with the element 2 away. Right? So now this element here is the sum of what? It's the sum of the first element plus the sum that it already had, which was the sum of the second and the third element here, right? So now the first 4 elements are correct, then the first 8 and so forth. And the only other thing that I want to point out here is that we don't need to worry about binary cases. Right? This is, again, the same size array. That we have 13 elements here, not a power of 2, but it doesn't matter. Right? By the time that we're done, this element here is the sum of, well, it's in yellow here, right? It's these 2 elements and these 2 elements and so forth, right? So it reaches all the way back, and if you can redo this diagram if you really want to. It's a useful exercise actually to do that. But you'll see that this is now the sum of all elements in the array. Right? So there's no additional binary condition to be worried about here. One reason that this example is interesting and slightly different to folding, if we think about folding again, when we were updating the values here, right, to update this element of the array, we were reading itself and this element here. In particular, we were not reading any element that was being modified by any other thread. Right? We needed the previous iteration to have completed, but there was nothing interfering with the results in this iteration. That's not true for scanning. So for scanning, if I'm, for example, updating this value here, right, which is the sum of these 2 elements, then this value here will be the sum of this value and this value, right? So this thread is reading something that's being updated by this thread, right? So we have an additional hazard, additional race condition. So there's 2 ways to do this. One is to separate this into 2 phases, right? First, all the threads read the values they need to read, we sync, and then all the threads write, and then we sync again. But synchronization is expensive. So if we can have avoid synchronization, that's better. So what I'm going to do is I'm going to show you an example of an implementation where we actually use 2 buffers. Like for folding, we were using 1 buffer, right, that we were updating in place. Here we're going to use 2, and only 2. So we're going to read from the first, write into the second, and then once we're done, we're going to flip the roles. So we're going to read from the second, write to the first, and flip and flip and flip until we're done. So let's look at the code here. Start the same way. We have some pointer to something on the device and the size. Now, this is a new Cuda feature that we haven't seen yet before. This is shared memory. So shared memory is, you can think of as cache memory, which is shared between all the threads in the block, right? Not across blocks, but within the block. And so we're allocating, we need to have a fixed size here, which is why I didn't pick n. Like we need to say exactly how much statically. So I just picked the maximum that's possible, 1024. And so all the threads in the block can read from the shared memory, and it's going to be much faster than reading from the global GPU memory. That said, for modern GPUs, you have to worry about this less because there's powerful caching in place, but sometimes this is still necessary. Again, we picked the thread index as our index. We're going to start reading from temp1 and writing from to temp2. Right? So this is our initialization here. Now, temp1 currently contains whatever it contains, right? So we need to initialize it. So all the threads are going to initialize the read one to be, like we're going to copy from the global memory into shared memory. We wait for all threads to do this, and then we start striding, right? Just like showed in the picture. If there is a value available, that's like we're reaching back now, right? Then we add to our current value. Otherwise, we're basically done with this value. It's already at the right value, and just we leave it as is. We do need to copy it, right? Because we're copying back and forth between these 2 arrays. We sync so that all the threads get a chance to complete, and then we swap the roles of read and write. And at the very final, all the threads are going to write their final value into the global array again.
Yeah.
And so let's do the rest. So we do the same thing again, right? We copy from so now we have 2 copies, right? We copy first from the main machine, the host, into the device, the global device memory, and then all the threads are going to copy again from the device memory into shared memory, right? And again, that only makes sense if you're doing a ton of calculation, which here we are not, right? I'm not really showing you idiomatic CUDA code. I'm showing you just to give a bit of a taste, like the kinds of things you might need to worry about. We invoke our kernel and we copy back. Okay, then on the Haskell side, again, we have a wrapper, right? And it's similar to what we did before, right? So we get a pointer to the input elements, we allocate an array, we get a pointer to that array, call our receive function, and construct a vector from it. Like there's nothing new here that we didn't already do in map. And then finally, the property that we have to test, and that is right, similar as before. We're calling our CUDA function. We need something to compare it against, but vector influenced scanning, right? It's just a pure Haskell implementation, and so that's just what we compare it against. All right, let's just try it. Compile our CUDA code, clean our Haskell code one more time, run the Haskell code one final time. And if everything goes according to plan, then all properties should pass. Yeah. And just to show you that this is really useful, because some of this CUDA code can get quite complicated, right? Like you might forget to synchronize. There are like this shuffle functions that get quite complicated sometimes. So just to show you that if I forget one of these synchronizations here, right, which is quite a bug that can quite easily happen, then if I just write a couple of unit tests for my function, right, then it's quite likely that I might never catch it, right? Because it might happen. It might just work. So, but now we're not going to run a couple of tests. We're going to run hundreds of tests. We're going to fire hundreds of tests at it. So if this is non-deterministic, then we are going to find a counterexample. Now I say that. Now I pray that it actually happens. It is non-deterministic, but yeah, it's already shrinking, right? And we get a very huge counterexample. And again, that's because it's non-deterministic, right? So perhaps it tried to shrink. After shrinking, it happened to do the right thing because that race condition didn't happen. And so it was not able to shrink any further. But yeah, so this is, to me, this has been invaluable for writing more complicated CUDA code. Have a simple Haskell implementation that might not be very performant, but is actually very simple to understand and compare it against them.
I think previously you also said that, if you run the tests again, then you get a different counterexample. But with a non-deterministic one, you can even run with the same random seed, right? And,
that's right. Yeah.
And that is an even stronger indicator that there is non-determinism, that if you get a different counterexample with the same seed.
Yeah, in fact, I should have done that earlier, actually.
Yeah.
So
now we cannot really see.
1360054 or something, the very final one. And now I'm passing the exact same seed twice.
You can already see that the
shrinking is much lower. So it must have gotten with a different example. Yeah, it's a totally different example here. Yeah. In fact, I should have done it earlier. Yeah, thanks for pointing that out. Yeah.
But it's I think you also kind of answered one of my questions. So I was originally thinking, like when I just saw the picture, I thought that
of scan.
Of scan, yeah. I thought, well, that looks almost easier than the picture for fold. Why are you not just doing this for folding as well? But I guess because you need the double memory, that is reason enough, right? That sort of like in the end you end up with a higher cost.
You mean could we implement folding by scanning?
Folding scanning is computing more strictly more information than folding, right?
So one thing that's important here is that all threads are working all the time here. Whereas with folding, that's not the case, right? These threads are working, and then only these threads, and then only these threads, and only these threads, right? So all the threads to the right, they're all stopping to work, right?
But so does that even buy you very much on a GPU that threads are not working?
Yes.
It does? Okay. Yeah, I don't have a good feeling for this.
Yeah, that's one reason that we are structuring this tree the way that we are structuring it, as opposed to the scan, right? so that we bundle all the threads that are not working together, sort of they're adjacent, so that entire warps of threads can be idle or not idle at the same time. But that is something to think about when you're writing highly performing CUDA code.
Yeah, so Mikolai is asking whether this is just like saving you power or temperature, or whether that means that these like idling threads can actually be potentially used for something else and at the same time.
They could, yeah. So what I've shown you, all the examples that I've shown you here are very, very simple, right? Like we have a malloc, a copy, then a kernel, and then a copy back, right? In general, that's not how it would work, right? You would have a malloc, a copy, and then you could spawn any number of operations, right? In fact, there's an example here. Now, this is not synchronous. When we start spawning kernels, if there's dependencies between them, we need to be careful about that ourselves. And so it's very possible to spawn two operations, and the second is waiting for some resource to become available on the GPU. And because we wrote our code in such a way that entire warps have become idle, more resources have become available earlier, and so new operations could already be scheduled on the GPU. So for a single operation, it doesn't gain you very much, but when you have a sequence of operations, you start really benefiting. Yeah.
Okay. Yeah. So thank you very much. Okay. Thanks for watching this episode of the Haskell Unfolder. If you enjoyed it, please like and subscribe. Feel free to leave any comments below, or like just now in the chat, which we'll leave open for another few minutes. And we'll be back as usual in a couple of weeks. We haven't decided the exact date yet.